Okay, I guess let's get started. So the exam is coming up this Wednesday, and the information is similar to what we have for the first exam. I guess I'll briefly go over it since you've already been through this. You don't need to. Say it again?
It's exam 1.
Yeah, this is exam 1 info. I didn't update it for exam 2, but I updated it in the last lecture, right? You had 2 slides on exam. Basically, you can bring 2 sheets, 2 cheat sheets. You can reuse your cheat sheet from exam 1 if you wish, or you can do 2 completely separate cheat sheets. But since it's not going to be based on memorization, hopefully your cheat sheets won't help you too much. Hopefully their job is to help you understand the material such that you can solve the problems. That's the reason for the cheat sheets, actually. But who knows? Maybe they'll help you. So it'll start at 12:30. So I'll follow the exact same thing except for the cheat sheets, basically, and except for the content of the exam. Anything is fair game, as we've discussed in the last lecture. Everything we've covered so far in this class, including the readings that I've asked you to do, are fair game, including all of the lectures. But the material will be skewed towards the material that we have not covered for exam 1, midterm 1. We'll go over the material briefly. But today, I've already given you ideas on how to actually study for the exam. And I'll repeat it again. Basically, solve the past exams. That's probably a good thing to do. Definitely study the material, because the questions will not be exactly the same as past exams. But solving the past exams will enable you to do practice on the type of questions that you will see, and it will also enable you to test how well you're doing on time. Don't panic. Time will always be an issue. That's true for pretty much everything in life today, right? Especially in the data-intensive world we're living in today. So intelligently using your time will be important. That's why I suggest that you actually solve the past exams, not only to get a good idea of what the questions could be, but also to get a good idea of how well you will do on time. Okay? That way you could adjust. And I would suggest be smart in solving the questions. If you're spending too much time on a question, just maybe move on to the next question that you're confident about, that you may become more confident about. But hopefully you're confident about everything in the course so far. Okay, let's see, what else? Well, you can look at this, and you can look at the last lecture's slides. So what is the material that we're going to mainly focus on? Let me tell you that, and then I can take questions about the material. So this, remember, the first exam covered until static instruction scheduling, although there was no real question on static instruction scheduling. There may or may not be a question in this exam. After that, we've covered a lot of memory hierarchy, as I promised to you. Actually, this was one of the questions that you asked in the review session. I think, what are we going to cover next? And we did cover a lot of memory hierarchy. And the exam will mainly focus on memory hierarchy. There will be a lot of questions on the memory hierarchy. Now you can imagine what those could be, right? Caches, locality, advanced caching mechanisms, memory level parallelism, the concept of it, how to exploit it. This is just to jog your memory so that maybe questions can come up. Main memory, how it operates, how it's organized. DRAM, some DRAM enhancements that we've talked about in the guest lectures, in Vivek's and Dongkyok's guest lecture. Remember the row clone idea, or tiered latency DRAM. These are all actually fundamental concepts. The ideas are building upon fundamental concepts, even though they're new ideas. Memory scheduling, different kinds of mechanisms to handle interference at the memory controller. How do you schedule requests from a single thread and multiple threads? You can see past questions on past exams on that. And then we wrapped up main memory. Other interference handling mechanisms, we've discussed that, right, briefly. Source throttling, mapping data to different channels such that you minimize interference across applications. We also discussed thread scheduling, potentially such that threads that interact nicely with each other are scheduled together such that they don't contend for memory at the same time, perhaps, or in a destructive way. And then we went into memory latency tolerance mechanisms. We talked about 4 fundamental ways of tolerating memory latency. Do you guys remember that? That's a nice potpourri question, right? It's really easy. It's almost a freebie. What are the 4 fundamental ways of tolerating memory latency? Yes?
I want to butcher these. Prefetching.
Good.
Caching.
Good.
Run ahead execution.
That's one enhancement over a more general paradigm, which is out-of-order execution.
Oh, I don't
Yes, that's right. Run-ahead execution is an enhancement over that.
Yeah, don't worry.
That's the 3. What is the 4th one? Multi-threading. It doesn't have to be fine-grained, any kind of multi-threading, yes. That's good. So you two together get 100% on the question. That's right. So multi-threading is another topic that we can ask you questions on. We've covered fine-grained multi-threading a lot, for example. And there's actually a question in a past exam you can study. So all of these topics we've covered in detail. We've covered prefetching. That's actually the next lecture after run-ahead execution. We've covered the 4 questions in prefetching. What, how, when, where, right? I guess why is not a real question. You could ask why. I guess we could ask that question as a potpourri question. What are the 4 questions in prefetching? And if you say why, it doesn't work. Anyway, that's a joke. So prefetching we've covered. We've covered different prefetching algorithms. We've covered all of the what, why, what, when, where, and how, right? What kind of prefetching to do? Hardware, software, thread-based. You've covered different kinds of prefetchers. Stream prefetcher, stride prefetcher, Markov prefetcher, content-directed prefetcher. And these all cater to different access patterns. Hopefully you're jogging your memory right now. So if I ask you what kind of cache misses can a Markov prefetcher not prefetch for, what would you tell me? You don't know? That's a good. What about you? Say it again. Compulsory misses. Yes, exactly. Right. So remember Markov prefetcher, it's correlated between different addresses. If it's seen multiple address pairs, let's say address pairs A and B consecutively missing in the cache, later it would say, oh, I've seen A followed by B before, so next time I see A, I'm going to prefetch B. By definition, this means that you should have seen the addresses before you can prefetch for them, which means that compulsory misses you cannot prefetch for, right? That's good. That's another good potpourri question, for example. Although you asked it in the previous exam, so you're probably not going to get it. I guess that's the advantage of taking the course later and later. You get more and more advanced questions. That's how knowledge grows in the world, right? Okay. The other latency tolerance mechanisms, we covered run-ahead execution, obviously, so you should know that well. Which means that you should know out-of-order execution well, even though it's a past topic, midterm 1 topic. You should know the execution paradigms we've discussed. GPUs are still fair game. Remember, I like asking that GPU question. I don't know if it'll happen in this exam or the final, but remember the GPU question in your first exam? Well, that's similar to past GPU questions, right? Once you understand the fundamentals, it's really easy. Okay, what else? And then we went into multiprocessors, and we covered different types of multiprocessors, why to do multiprocessing or parallel processing in general. And there were 3 reasons for that too. That's another beautiful potpourri question, right? What's the reason to do multiprocessing? One is performance enhancement, obviously. Yes? Power reduction, yes, that's one. Actually, 4 reasons, I should say. The performance is obvious. It's kind of a given, yes.
Complexity reduction.
Yes, reducing complexity, improving scalability, reducing cost. And we've discussed in detail in the multiprocessor lecture. Yeah.
Is that the same thing as like the yield?
Yeah, you could think of it that way. That's right. You could improve yield because you have a much less complex circuit that you can verify much more easily. That way, it's likely that you'll get a multi-core processor correct compared to a single-core processor. Yes.
Is that the same thing though as like having the redundancy?
No, that's different, right? That's the third reason to do parallel processing, in addition to the obvious performance reason, to improve dependability by having these redundant units that units that do the same computation redundantly, and comparing the results of those units, you can improve the dependability. And that's a very fundamental reason. So you can imagine questions related to this. So we've covered why to do multiprocessing, and then we've covered like how to do multiprocessing. We've discussed, for example, tightly coupled versus loosely coupled multiprocessors. And you remember what's the key distinction between them, right? Yes?
Whether or not they share memory.
Yes, which one shares memory?
Tightly coupled shares memory.
That's right. Yeah, tightly coupled multiprocessors have a global shared address space, whereas loosely coupled multiprocessors communicate via message passing. They don't share memory. And that's very fundamental too. And then we've talked about a lot of issues in multiprocessing. One was the issue of, well, we've discussed some of the metrics, for example, utilization, redundancy, and efficiency. We've discussed parallel speed up. We've discussed Amdahl's law again. We've discussed what superlinear speed up is and how you can get superlinear speed ups. So you should be very comfortable with computing speed up, for example. That's relatively easy. So if I give you the same question, remember the question I gave you, the polynomial computation, where I asked you to compute the time it takes to do this polynomial computation with one processor versus 3 processors? You can probably come up with the best algorithms to do that now. And the answer was 1.6, not 2.2. Speed up with 3 processors was 1.6, not 2.2. Okay, you can look at the lecture notes for that. So we've covered that. And then eventually, well, what else did we cover in this lecture? Yeah, we covered the multiprocessor metrics. And then we talked about what Amdahl's law doesn't cover, right? Amdahl's law shows that serial portion of the program is a bottleneck for parallel performance, right? Your parallel performance is limited by the serial portion. And you can calculate what's the maximum parallel performance you can get given a program, right? Because the part that you cannot serialize, the part that you cannot parallelize dominates your speed up. But there's also bottlenecks in the parallel portion. This is another great potpourri question, really simple. Give me. What are the 3 major reasons why the parallel portion of a program is not perfectly parallel? Yes.
Resource contention.
That's 1.
Synchronization.
Synchronization. 2. There you go. 3. Is there a 4th one? If you find a 4th one, let me know. So far, nobody has been able to. Everything else you can translate to one of those. Okay? And we've covered all of those issues. Well, we've definitely covered resource contention in detail, especially in memory scheduling. We've covered load imbalance as examples. Right? Remember the example that I keep giving you. If you're counting the number of occurrences of a letter in a book, you can divide that task into multiple threads where each thread examines n number of pages of a book. And you can easily get load imbalance if you divide the problem this way, because some thread can get pages that are empty, right? And it has no counting to do. As a result, you have a lot of load imbalance. And your parallel program is not perfectly parallel now. Your parallel portion is not perfectly parallel because one thread doesn't have any work to do. So the processor that you allocate to that thread is doing nothing, whereas all of the other processors have all of the work to do. Okay? And then we covered consistency and coherence. These are more advanced topics, but they're clearly very important topics. We covered the importance of ordering, memory ordering in multiprocessors, building upon the ordering of instructions in single-core processors, which was an important issue in precise exceptions, if you remember. And we've covered what kind of problems that you can get if you don't have restrictions on ordering of memory operations coming from different processors, right? If all processors follow the von Neumann model and there's no other restriction, you can get an incorrect result. Remember that synchronization example that I gave in that lecture? And to solve that problem, we've discussed the idea of sequential consistency. Right? Sequential consistency says that all processors see the same order of memory operations, and the hardware satisfies this. And once you have that, you don't have any inconsistency across different processors. As a result, you can guarantee that synchronization operations are ordered the same way for all processors, and you won't get an incorrect result for that example, or for any other example, actually. You guys remember that? Okay. And we've discussed that it's maybe actually too strong of a requirement, right? Although we didn't discuss in detail what are the other potential consistency mechanisms. You don't really need a global total order across all memory operations to be, and all processors to see that exact global order, because that may be too strong, right? Sometimes you don't care. For operations that do not affect synchronization, for example, you don't really care in what order they occur. If processor A is not affected by these operations, why should it see the same order, right? So we discussed the idea of weaker consistency models that relax this order for operations that do not really need to be ordered, and that enforce this order for the operations that really need to be ordered. We talk about acquire-release consistency model, for example. We talk about inserting memory fences that ensure that the operations are actually seen by other processors using the weaker memory consistency models. But we didn't really go into detail on that, so I'm not going to test you in depth, although you should be able to reason about it. And then we went into another issue, coherence, right? If you have caches in a multiprocessor, how do you keep those caches data coherent for a given block? So the key difference between consistency and coherence is consistency is all about ordering of all memory operations regardless of the address, whereas coherence is about ordering operations for a given memory address or a cache block. And we talked about different protocols to keep the caches coherent. One was a really basic, well, there are two major approaches, right? One is Snoopy bus, Snoopy cache protocols, where you assume a single point of serialization for all memory operations, and all memory operations, all caches see the reads and writes that happen from all processors. And they snoop the bus, and if they have the data that's being the block that's being written to, they can actually keep the cache coherent because they see all of the requests. That was Snoopy bus. And the other option was directory-based protocols, where you have an agent or middleman, if you will, that takes requests from all caches or all processors and arbitrates them. And it keeps track of which caches actually have a given block, and it can keep the caches coherent. And there are two methods of coherence also. One is update-based and the other is invalidate-based. Right? When you figure out a cache has the block that another cache wants to write to, let's say processor A and processor B. Processor B has both of them cached block X, let's say, and processor A wants to write to block X. Then the key question is to keep both caches coherent, there are two actions you can do. You can invalidate block X from all of the other processor's caches. That's an invalidation-based protocol. Or when you update your own cache, you can update all of the other caches. That's an update-based protocol. And we've discussed trade-offs. If, for example, the other cache is going to need that data that's being written to, maybe update-based protocol is a good idea, right? Because the other cache is going to read the data that's this processor is going to write, or this other processor. When I talk about cache coherence, it's processor and cache. I use them interchangeably because they're coupled, right? Or you can have invalidation-based. If the other processors are not going to read the data that's going to be written by this processor, maybe you want to invalidate all of that data. And these update or invalidate-based protocols can be applicable to either the Snoopy bus or the directory. Directory, for example, can say send invalidations or updates. Right? These are orthogonal concepts. Make sense? You remember the directory, right? We went through the directory in good detail. And then we talked about protocols, which are again orthogonal to whether or not you do Snoopy bus-based cache coherence or directory-based cache coherence. You can have valid-invalid-based protocol. You can have MSI, the three-state protocol, modified, shared, invalid. And then we figured out what is the problem with MSI. Whenever you fetch a cache block, you get it in this shared state, right? shared state means the block is clean, but potentially another cache may have the block. Which means that if you want to write to that block, you have to broadcast an invalidate to all of the processors. If that block is the only copy in the system, that invalidate wastes a lot of bus bandwidth. So to get rid of that problem, we added the state called E-state, exclusive state, which means that the block is clean, but it's exclusive to this cache. So if a cache fetches that block, and if that's the only copy that's being cached in the system at that point, then it can get the block in exclusive state. And whenever it writes to that block the next time in its exclusive state, it doesn't need to broadcast an invalidate to any of their caches. Make sense? So we talked about this exclusive state, and then that led us to the MESI protocol. And you can implement MESI in a directory-based protocol as well. Right? It doesn't need to be a bus-based, because again, this is a higher level protocol. Yes? Say it again? Oh, I see. That's a good question. No, you don't need to memorize anything, but if you're able to reason about it, that means that you can actually draw that graph, draw that state diagram. So you don't need to memorize the details. You should be able to reason about it. But for example, if we give you a MESI protocol and if we say what's wrong with this state diagram, you can solve that by reasoning about it. I guess another option could be memorizing it and solving it, but that gets tricky, because what if we change something in the protocol, right? Because all of these protocols are slightly different in real implementations too. And then we talk about Moesi, right? That built upon the downside, one disadvantage of MESI, which means that when you're going from shared to modified, or actually modified to shared, you need to write back the data to memory, because there's no state that says this is shared and this is dirty. Right? And then we added that state, O state. A cache block can be an O and M state in different caches, and that state now says the block is shared and potentially dirty. Actually dirty, not potentially dirty. Okay, you can remember that. But we didn't go into the detail of Moesi protocol. In fact, you're going to implement the MESI protocol in your lab, which is already out. How many of you have started implementing it, by the way? No? There you go. There's at least one person. Okay. And after that, we talked about, in the guest lecture, we talked about performance predictability and cache compression. Did you guys like that lecture? Was it interesting? So it takes the concept that we've covered to the next step. And it shows that these are actually active areas that people are currently working on. These are my PhD students. Lavanya talked about how to provide predictable performance, or at least some steps in providing predictable performance. And Gennady talked about how to do cache compression. So you know the idea of base delta immediate cache compression? No? It's a pretty cute idea, right? You can, if the words in a cache block have low dynamic range, which means that they're close to each other in terms of value, you can encode that cache block as a single base plus small deltas from that base. Right? That way you can have a much smaller encoding compared to if you actually had the full words in the cache block. That's the key idea. And if most of your cache blocks are like that, then you can actually have a cache that's compressed. This hopefully leads to placing more blocks in your cache, which may increase your hit rate, which saves memory bandwidth also, because now you don't go into the memory as often as before. Right? Yes?
Is that just a less complex version of like memory compression that they do right now in operating systems?
So, you mean the algorithm itself, the compression algorithm itself?
Yeah.
Yeah, there are many compression algorithms. Today, what happens in memory compression in operating systems is it's a software-based, software-only compression mechanism. So they can use complicated algorithms to do that. And the latency in memory is long, right? Whenever you bring a page from the disk into memory, you can do that compression or decompression. but you can tolerate that latency. This is, you need a much less complicated compression algorithm if you want to do this purely in hardware. Because if your cache is compressed, if you, let's say, use a very complicated compression algorithm like LZW compression, which compress uses, decompression takes a long time to do that, because now you need to consult a dictionary to actually do the decompression. And if you want to do that in hardware, that takes a long time to decompress a cache block. Whereas that's a very latency critical part. With base delta compression, decompression was relatively simple, right? You have a single base, you can add to that base all of these deltas in parallel, which is basically a vector add, right? Instruction. Or vector add hardware. Okay. But you should know about the benefits of cache and memory compression, right? If you have a compressed cache, there are some benefits to it. You get hopefully better cache hit rate, hopefully reduced memory bandwidth usage because you get better cache hit rate. Well, there are downsides to it also, right? Because now, whenever you access the cache, you need to decompress the cache block first, which takes time. So your cache hit latency increases. And your complexity in the cache also increases, because it's easier to have a non-compressed cache than a compressed cache, because a compressed cache requires a compressor, decompressor, and some changes to the cache organization such that you can have compressed cache blocks. Right? Does that make sense? Okay, I think I've covered very quickly what we've covered so far after the first exam. Should I keep throwing out the ideas, or do you want to ask questions? Yes, there's one question.
Could you go over the part how PowerBS scheduling works?
Okay, I can do that. Let's see, I'll open from here. So the goal in PowerBS is twofold. The motivation is really to preserve parallelism, bank-level parallelism of threads, right? And we've discussed that. Actually, Justin discussed that on my behalf over here. Basically, if you have a scheduler that's not aware of parallelism, it can destroy the bank-level parallelism of each thread. Do you remember this example from the lecture? Basically, you have two threads, A and B, sharing the DRAM, and you have two banks. Assume that these are the requests that go to different banks, and if your scheduler services the request in their arrival order, it can take thread A's request to bank 0 first, and then thread B's request to bank 1 next, serve them in parallel in the banks, and then once thread A's request to bank 0 is done, it can schedule thread B's request to bank 0, and then once thread B's request to bank 1 is done, it can schedule thread A's request to bank 1, and then service these threads' requests in parallel again in the banks. So this is the baseline scheduler. What this scheduler did was it was not parallelism aware. Right? It did not try to preserve the parallel requests of a thread and serve them at the same time in the banks. As a result, both of the threads stalled for 2 bank access latencies, right, approximately. Now, if you had a parallelism aware scheduler, what it would do is it would preserve the parallelism of each thread. Let's say it gets the same request from these threads, and first schedules thread A's request to bank 0, and then it realizes that it has thread A's request that goes to bank 1. If it services these 2 requests in parallel, thread A can make progress because its request will finish. So it schedules thread A's request to bank 1 at the same time, well, in the next cycle. And later, thread A's request to bank 0 completes, and then thread A's request to bank 1 completes, and the memory scheduler can take thread B's request and schedules them consecutively to the banks. And while thread B's requests are going on, being serviced in parallel, now thread A can continue its computation because its requests are serviced in parallel and done. Right? That's the benefit of parallelism-aware scheduler. That's one of the key concepts in PowerBS, right? To preserve the parallelism, bank-level parallelism of each thread. As a result, you can improve performance. Why? Because if you look at this top part, each thread stalls for approximately 2 bank access latencies, whereas here, on average, threads stall for 1.5 bank access latencies. That's the benefit. So this improves system throughput. And that's the idea of parallelism awareness, right? We've discussed. How do you achieve that? You can schedule a request from a thread back to back. The downside of this is it can cause starvation, right? Because if you schedule a thread requests back to back, that thread may be generating lots of requests. As a result, soon after, you may be servicing only that thread's requests. So to prevent that, there's a second idea, orthogonal idea of batching, request batching. And the idea over here is you group a fixed number of oldest requests from each thread into a batch and service the batch before all other requests. Basically prioritize the request from this batch over every other request. Now this ensures forward progress, right? This is actually a very fundamental principle. If you want to ensure forward progress, but still do some reordering, you create a batch, do the reordering within the batch, but never do reordering across batches. This ensures that that batch that you created will complete before anything else in the system. And you make forward progress because the oldest requests are in that batch. That's the idea. In fact, disks employ this. For a long time, disks have employed this batching idea. Disks don't have the parallelism issue because they have parallelism issue, but they don't take that into account. That's all another lecture. What's the difference between memory and disks or SSDs? SSDs are closer to memory than disks. But that's the second principle, basically. So if you look at this, well, the purpose of this is to eliminate starvation and provide some sort of fairness. The purpose of this is to improve performance or system throughputs. And we've seen this example. So how do you actually do each of these? Well, batching is easy. You mark some number of requests, the oldest requests from each thread to each bank as part of a batch. You can have a single bit that marks each request. And the requests that have that bit are prioritized over others. How do you do parallelism awareness? Basically, the idea over there is to rank the threads. When you form a batch, also form a ranking of threads, which I will show you over here. Basically here, the memory controller, let's say, has all of these requests queued up in its memory request queue. It forms a batch, and a batch is formed based on this threshold called marking cap, which you hopefully remember. And within this batch, it forms a ranking. And that it prioritizes the threads based on that ranking. Let's assume that thread 0 is ranked over everything else, so the memory request schedules thread 0's request first. And in the meantime, other requests arrive, but they're not included in the batch. Because if you keep including requests in the batch, there's no point in batching, right? You don't get the starvation freedom guarantee. Then thread 1's requests are ranked over others. They get completed next. And then thread 2's requests are ranked over the others, or other threads. They get completed. But remember, see that thread 2's requests that are outside the batch don't get completed because this batch is prioritized over other batches. And then thread 3's requests, thread 3 is the lowest ranked thread. They get completed. After that's done, the memory controller forms a new batch. And the reason this works is bank latencies are much longer. So requests get queued up. So you can form these batches. Does that make sense? Yeah. And we went into more detail. So if you want more detail, you can actually, I don't know if you want me to go through that, but these were the key concepts. The more detail is an implementation of it. How do you actually implement this? And we've given you this example of how to actually really rank the threads and how to do the batching. Yes?
Do they use these as processors? Because like on Friday, the first lecture, she was saying like it doesn't, like it adds so much complexity that it's not practical.
So that depends. That depends on what you want to achieve. Most processors today use a variant of the FR-STFS policy that we discussed, row bit first policy. But some of them incorporate batching. And I'm not at liberty to tell which ones incorporate batching, and they're not going to tell you whether they incorporate batching. But batching is a relatively simple concept. It is true that more complicated ideas are more difficult to implement.
Can you do batching without priorities within batches?
Yes, you could do that, right? That guarantees some starvation freedom. So you could, for example, have batching, and within the batch you can still employ FRFCFS.
Yeah, because she was saying it like the ranking mechanisms just add a lot of complexity.
Exactly,
Right?
yes.
So it just like adds too much latency.
Exactly. Maybe you don't need to do a full ranking, but you do something simpler.
Okay.
But this demonstrates the concept of parallelism awareness and why that could be useful. And maybe you can come up with an easier way of implementing this. Not necessarily like this. An easier way maybe not to form the full ranking, but let's say you pick a thread and prioritize its requests, and then you pick another thread and then prioritize its requests, and then pick another thread and prioritize its requests. That way you don't explicitly form a ranking, but you kind of get the effect of parallelism awareness, right? So you can imagine, once you have the concept of parallelism awareness perfectly shown this way, how do you achieve an approximate implementation of it? That's what I would like to give you in this course. The concepts and then implementations, hopefully you can approximate. But that's a very good question. And you've seen the blacklisting memory scheduler, right? That Lamaya talked about. That was another idea. So you can imagine different ideas. The idea over there was to... so that's another idea that's kind of similar to batching, but not exactly the same. Batching ensures that you have strict starvation freedom. Lamaya talked about a memory scheduler called blacklisting memory scheduler, which is actually much more easily implementable. Not compared to batching, but parallelism awareness. But the idea over there was if you have serviced some number of requests from a thread, let's say n, blacklist that thread. Say that this thread is deprioritized for a while. Other threads for which you have not serviced that many consecutive requests are prioritized over this thread. This way you can get rid of some of the downsides of prioritizing one thread over the other for a long time. Oh, am I? Thank you. Okay, what else? I guess that hopefully answers your question. And there is actually a question in one of the midterms. I think in one of the past year's midterms that asked you to compute how long it takes to schedule these requests with FRFCFS and PowerBS, I believe. I'd encourage you to solve that.
That was on the homework.
Oh, that was on the homework too. That's right, yes. I confuse what we put on the homework and what we don't. That's actually an easy question, right?
Once you know how that works.
Yeah, once you know how it works, it's easy. That's right. Okay, what else? These are pretty fun topics. These are actually topics that people are struggling with when they're designing multi-core processors. This is the complexity of a multi-core processor that doesn't exist in a single core processor. You need to somehow deal with interference between different threads. And if you go to a company, you'll be dealing with these things as well. If you design the cache, for example, if you design the memory controller, these will be issues that you'll be facing. So you may need to apply batching, for example, when you design the cache of your next super duper multi-core processor. Yes?
No.
Sure, yeah, we can. Oh, you had a question? Or?
No.
Okay. What else? Does that mean I can assume everybody knows everything? No? Depends. Depends is a good answer. Yes. But it doesn't always depend. So be careful on the exam. We've covered a lot of caches, so I definitely encourage you to know caching. Know how to compute the tag store size, for example. That should be pretty trivial by now. Know how to compute the cache hit rate for different access patterns. And there are questions on the past exams. I'd rather not solve them so that you can actually solve them and try to get them right. But you can find a variety of caching questions from past exams. What we're going to ask is not going to be fundamentally different. Of course, the question would be different. What else? Know how a DRAM is organized? Remember the subarrays? Right. We've covered subarrays quite a bit, especially when we talked about row clone and TLDRAM. Vivek gave a good overview of subarrays. Yes?
I guess would we be able to go over like briefly DRAM organization and stuff like that?
Sure, we could do that. You guys want to do that? I guess you want to do that. That's enough. Oh no, this is not the right one. At what level? The DRAM bank organization? Well, I guess we can start with this. Oh. Let's see. Well, we covered the bank quite a bit, right? The bank abstraction itself, right? Even this is an abstraction, so we're going to break that. But if you start from the subsystem level, DRAM is broken down into this kind of organization. At the top, you have the channel, and then you have the DIMM, rank, chip, bank, row, and column. We could do a top-down organization. Well, you know the bank operation, so I'm not going to go over the bank operation. Let's go over this top-down view, right? Or should we do the bottom-up view? No, let's do the top-down view. Is that what you wanted?
Okay.
Yeah, let's start with this, and then we'll go over the internal. So at the top, you have the channel, right? If you look at a processor, you have these different channels. They're completely independent of each other. And from each channel, you can have multiple DIMMs hanging off. And if you add more DIMMs, you actually get more capacity. And what is a DIMM? A DIMM basically looks like this. It's basically consists of multiple ranks, right? It's gonna, in this case, you have two ranks, rank 0, rank 1. And remember what a rank was. A rank is a collection of DRAM chips that respond to the same command. It's like a rank of soldiers. You say read, they all do read, but they provide different pieces of the data. Why? The reason is each DRAM chip has a narrow interface. For each chip, you get 8 bits out of the chip. This is to reduce the chip cost. So if you want to get 64 bits in one access, you put 8 chips together as a rank. You send the same command, same address to them, and they respond with consecutive 8 bits. Make sense? That's the idea of a rank. And you can break down the rank. Well, this is ranks obviously share the memory channel, and each rank responds to the same address and same command, but different ranks have a different chip select. In this case, you need to you don't need to activate both of them at the same time. And a rank consists of multiple chips, as I discussed, and they all provide different pieces of, in this case, the 64-bit data. And then a chip consists of multiple banks. Right? Basically, each of the banks can provide, in this case, 8 bits, but you can get only one of the 8 bits in a given cycle. You can start the access to different banks in parallel, but you pipeline the accesses over the data bus. So they share the address, command, and data buses in a pipeline manner. Make sense? And we remember this is the bank itself. Bank is organized into rows and columns, and you have a row buffer. Again, this is a logical structure. So let me go into the, we've broken this down into an even lower level organization, which was discussed in this lecture. Okay, I guess I'll go over here. You want me to go over this? Sense amplifiers? Okay, that's fine. But I'll give you the, well, you can go over this. You can actually look at the lecture itself. But the cell operates this way. So Subarray is a building block for the DRAM bank. So a DRAM bank I showed you over here, it consists of rows and columns. But even that's an abstraction, because if you want to have a large bank, where is this? Last time I threw away many of these. As a result, we have 0. There's one over here. Ideally, you would like to have large capacity, right? You would like to have many rows. And you would like them to be connected to these sense amplifiers. And the problem is if you have, let's say, 32,000 rows in a DRAM chip, This means that you have 32,000 cells connected to a bit line, and that bit line is connected to a sense amplifier. And whenever you read a row, whenever you read a cell, that cell drives this bit line, perturbs the voltage on the bit line that needs to be amplified by the sense amplifier. If you have so many cells connected to a bit line, you have a very long bit line. As a result, you can have very high capacitance on this bit line. And this leads to two problems. One is you have high power consumption. The second is latency would be higher because you need to drive a much longer bit line, much longer interconnect. The third is sensing becomes much more difficult because you have a long bit line, you need to have stronger drivers to do that. So as a result, to reduce the latency as well as to make sensing more reliable, what DRAM manufacturers do is divide this bank into subarrays. Come on, we should be able to have better. Do we have something else over there? These things don't work. Yeah, thank you. Let's see. Let's try these. Okay, much better. So instead of having these really long bit lines, for which you have 32,000 cells connected, the bank is divided into smaller structures called subarrays. Now in this case, I don't show all of them, but each of them, let's say, have 1,000 cells connected to it, and you have sense amplifiers for each subarray. So basically, the bank that I showed you earlier was an abstraction. It really consists of, in this case, 32 of these subarrays, and for each subarray you have a sense amplifier. And the reason for this is now your bit lines within the subarray are much shorter because these bit lines do not need to be connected. Basically, you access a row in a given subarray, and that row is driven and sensed by the sense amplifier that's for that subarray. Why divide the long bit line into short bit lines and have subarrays? Well, now these bit lines are much shorter. Right? So your latency is smaller, your power consumption is smaller, and your reliability is better because hopefully for the same sense amplifier you can sense much more reliably. Make sense? And basically with this subarray now you have the row cached in this row buffer. Then the question is, how do you actually read some data from that row? Basically you have some other bit lines called global bit lines, of which there are much fewer, that actually go across all of the subarrays and go into the I/O circuitry of DRAM. Basically, when you activate a row, what happens is you activate the row, and the row gets latched and sensed in the sense amplifiers of the subarray. When you do a read, the column that is in the sense amplifiers get driven by the global bit lines to the I/O circuit. Make sense? And these global bit lines are actually much wider than the local bit lines because they need to carry data for much longer distances. So to be able to reliably do that, these are actually much wider, and they consume more power. So that's why you have fewer of these global bit lines. In fact, they could be 64 of these global bit lines that are driven. Whereas, remember, a row could be 1K bits, right? So when you activate a row, you actually activate these smaller local bit lines, and you sense the data on those local bit lines. So that's the idea of a subarray. And this is an example subarray, basically. And then you put these multiple subarrays. Well, this is what I showed you, actually. You put these multiple subarrays together. This is one subarray, this is another subarray, and then this is the bank I/O. That's the global bit lines. Okay. Is that good enough? So know why there's a reason for the subarrays. If you want to have a large bank, you cannot have very long bit lines, so the large bank is divided into smaller subarrays, which have shorter bit lines. And then there's this other circuitry that we've discussed. But you can take a look at this lecture, I think. This is exactly what I told you over here, except it doesn't show the global bit lines really well, I guess. Okay? What else? And the idea of row clone, I guess I'll give you that also. The idea of row clone takes advantage of this bulk operation. Basically, if you want to copy one row to another in DRAM, purely in DRAM, what you can do is you can activate this row, which brings the row into this sense amplifier in the subarray. And if your destination row is in the same subarray, let's say you want to copy the source row A, to destination row B, and they're in the same subarray, what you can do is activate the source row, which brings the data into the sense amplifiers. Now sense amplifiers have the charge and they're driving the bit lines. After that happens, you can activate the destination row. Once you do that, the charge on the bit lines drive the cells in the destination row because the bit lines are much stronger. The sense amplifiers are much stronger than the cell. Remember, the DRAM cell is very small. It contains very little charge. Whereas the sense amplifiers are much larger, much bigger. In fact, a sense amplifier today is more than 100x times the size of a cell itself. So if you have a sense amplifier, and while the sense amplifier is driving the bit line, if you activate the cell, what this means is you basically have, this is your capacitor, this is the cell, and this is your access transistor, and this is your bit line, and your sense amplifier over here is driving the cell. Let's say it has a value of 1. This has VDD. And when the bit line has VDD and you activate the cell, what happens is through charge sharing, this VDD charges the capacitor. So you get the value in the sense amplifier latched into the cell. Right? Cell gets charged. Capacitor gets charged. As a result, the value in the sense amplifier gets copied into the destination row. That's how you can achieve a copy, row-to-row copy in DRAM. That's the idea of row clone. Make sense? So once you know the DRAM operation, this is all really simple. What else? I know you didn't ask about row clone, but I volunteered it. What else? So the idea of tiered latency DRAM is to basically even go further in this division. Basically, the reason DRAM latency is high is the access time it takes to activate a row is long because the bit line is still long. Even driving 1000, like a bit line that has 1000 cells hanging on it, is slow. Let me actually go to those slides. Because 1000 is a larger number than 32, right? This is what we talked about. Basically, yeah. This is what you have today. In a subarray, you have, let's say, 1000 cells connected to a bit line, and you have a sense amplifier connected to that bit line. This long bit line is slow because this bit line is long, it has high capacitance, right? To make it faster, you could do something like this. You could chop up the bit line into smaller bit lines and have sense amplifiers, basically smaller subarrays, right? Now, the upside is this is faster, obviously, because whenever you do an activate, you drive a shorter bit line, right? The downside is obviously what's shown in this figure. Now you have huge sense amplifiers. As a result, it's much bigger also. So you have a trade-off between latency and area. And this is what we've shown to show that. Commodity DRAM has 512 to 1000 cells per bit line. As a result, it has high latency, but small area. If you want to reduce the latency, you can reduce the number of cells connected to the bit line. If you make it 32, your area shoots up, but your latency reduces. Right? In fact, you can get some fancy DRAM today in the market that's called reduced latency DRAM or fast cycle DRAM that basically does exactly this, except if you want to buy it, you got to really pay more money. These are used in expensive routers, for example, because they do want to reduce the latency of packet processing. As a result, some of them use reduced latency DRAM to minimize the memory access latency. But in commodity machines, if you use them, your machine cost will go up. So ideally, you would like to achieve kind of the best of both worlds. Ideally, you would like to be here, right? If anyone tells you that they've designed a memory that is right here without any other costs, then you should tell them, tell me more. Because that's probably magic. So how do you approximate the best of both worlds? That's the idea of TLDRAM. And the idea is, remember, if you want to approximate the best of two things at the same time, heterogeneity is a good answer. And the idea of TLDRAM is a heterogeneous substrate. Basically, you have long bit line that has small area but high latency, short bit line that has low latency but large area. How do you get the best of both worlds, or approximate the best of both worlds? Well, let's start with this long bit line such that we get small area. Well, let's try to get a portion in that long bit line that looks like the short bit line. So let's isolate this little part over here from the rest with these isolation transistors that we can turn on and off from the memory controller. Now this creates an area that's fast, and this gives you high capacity with the addition of these additional transistors. That's the idea of this tiered latency DRAM. You get small area using long bit line, but you also have a low latency portion. When you disconnect these isolation transistors, the bit line looks small, right? Because sense amplifiers only see this part. The rest is not connected. Now you have two tiers in DRAM. One is the near segment, the other is the far segment. Near segment is fast and energy efficient. Why is it energy efficient? Because driving these long bit lines actually consumes more energy, because the long bit line has much larger capacitance, right? And you remember the power equation, right? This is dynamic power is proportional to capacitance voltage square F. Well, long bit line has high capacitance, and there's this activity factor, depending on how often you switch the bit lines. Okay? That's the idea, basically. If you want to access the near segment, you turn off the isolation transistor. That's what the sense amplifier sees, so it's fast. Reduced bit line length, reduced bit line capacitor. Well, I'm going through this really fast because you've already gone through it, hopefully. If you want to access the far segment, you turn on the isolation transistor. Now you can have large capacity also. But you get long bit line length, large bit line capacitance, and there's additional resistance of the isolation transistor too. So your latency increases compared to a commodity DRAM. And you remember Don Kyok showed you some latency and area evaluation, which shows that near segment access latency is much smaller than commodity DRAM, that is homogeneous bit line. This is 512 cells per bit line. In the near segment, if you have 32 cells per bit line, the access latency is 56% less. In the far segment, you have 480 cells per bit line. The access latency is 23% higher compared to homogeneous subarray. Why is it higher? Because you have additional resistance when you enable these transistors, right? Isolation transistors. And the power is very similar, which means that now you've got to be intelligent in managing this heterogeneous subarray, right? You have this near segment, far segment. If you want to get the latency benefits, you'd better keep the data that you've accessed frequently in this near segment. And how can you do that? Well, one idea is caching, right? If you actually use this as a very well-managed cache, if you have good locality, that's great. Keep most of your data in this cache over here. Make sense? And Don Kyok has given you lots of other stuff, so you can take a look at that. Okay. So that builds upon the DRAM structure observation that we've seen. Long bit lines are slow, short bit lines are fast. Long bit lines are energy inefficient, short bit lines are energy efficient. But long bit lines provide you higher capacity, whereas short bit lines don't. Okay, what else? I'll go back to the list of topics, if you will. You guys know about run-ahead execution? No? You remember the idea, right? You want me to go over it? Okay, so the basic idea is, well, I guess I'll give you with a single slide. Memory latencies are so long that it's hard to tolerate them with a small instruction window, right? And when you have a long latency instruction, it blocks the retirement because you cannot retire that instruction and any other instructions after it because you need to maintain the von Neumann model. And incoming instructions fill the window. Once the window is full, processor cannot place new instructions into the window. That's called a full window stall. And once you have a full window stall, you can it prevents the processor from making progress in the execution of the program. Run-ahead execution is a way of not stalling the full processor when you actually normally need to stall. Basically, this is an example I'm going to skip. Instead of stalling the processor when the oldest instruction is a long latency cache miss, what we do is, when the oldest instruction is a long latency cache miss, you checkpoint the architectural state and enter in mode just to purely speculatively process the instructions. Well, what does this mode mean? In this mode, you speculatively pre-execute the instructions. The understanding is that the goal is to just get prefetching. Pre-execute the program such that you can get to those cache misses that you would otherwise not have gotten to because your window is small, such that you can start those cache misses early. And eventually, at the end of this mode, when the original cache miss that led to this run-ahead mode returns back from memory, you go back to the checkpoint and reprocess all of the instructions. Make sense? So it's purely speculative. And the purpose of this execution is to generate prefetches. And the important thing is, if you have instructions that are L2 miss dependent, the original cache miss, for example, you mark their result invalid in the cache, as well as in the registers, such that you know that these results are actually bogus because you don't have the data, but you keep processing. And then you get them out of the window. So basically, you keep getting instructions out of the window such that you can make more space in the processor pipeline for these speculative instructions you can process. Yes? Oh, window. Okay. So you need to study the instruction window first. Basically, the instruction window, as we've defined, is all of the structures in an out-of-order processor that are needed to store the instructions that are decoded but not yet retired. You can think of this as the window of instructions that are currently in the machine. A pipeline, a part of the pipeline, definitely pipeline is that, but reorder buffer, for example. Right? Reorder buffer actually is exactly the window. It stores you put an instruction to the reorder buffer and it's decoded. You take it out of the reorder buffer when it's the oldest instruction and it's done. Right? So reorder buffer stores control state for all of the instructions that are decoded but not yet retired. But if you want to enlarge the size of this window, it's not enough to enlarge the size of the reorder buffer, because reservation stations, for example, those have some instructions that are decoded but not yet retired, so you need to enlarge the size of the reservation stations. You need to enlarge the size of the physical register file, for example. Reservation stations are similar to the physical register file. So enlarging the size of the window is difficult, because remember the out-of-order execution lecture? As you increase the size of your reservation stations, you need to increase the length of the tag broadcast and data broadcast buses that you have. So it's difficult to enlarge the size of that. Instead, why don't we build a small window and do something like run-ahead execution? That was the idea of run-ahead execution. In this mode, you need to get out of, if you have a small window, you cannot add more instructions into the window unless you get them out of the window, get some of them out of the window, and that's how run-ahead execution gets instructions out of the window. It drops the instructions that are dependent on cache misses. And when the original miss returns, run-ahead execution restores the checkpoint and resumes normal execution. So if you want to understand this well, I like this figure basically. If you have a small window, this is what happens. When you get a long latency cache miss, you execute some instructions, but then that latency, the window stalls. You cannot put in more instructions into the instruction window because now your reorder buffer becomes full, right? Because you have a small window. As a result, you get a stall. No more instructions enter the pipeline. You stall until this load retires, and it retires only after its miss returns from memory. Now you can get rid of the load from the window such that you make one space for the next instruction. And you can continue fetching instruction until you get a load to miss. Same thing happens after that, right? So the idea of run-ahead execution is, instead of stalling when you get this long latency cache miss, when this long latency cache miss instruction becomes the oldest instruction in the window, you take a checkpoint. And the checkpoint consists of the register file state, program counter, for correctness reasons, because you're not going to go back to that, and some other things that we've discussed, like the global branch history register and the return address stack for performance reasons. Because that's related to the context at this point, right? When you go back and re-execute instructions, you'd better have the same global history register, because that reflects what your branches were at this point. You don't want to pollute it. And the processor enters this mode where it speculatively processes instructions called run-ahead mode. Now it can get rid of this load 1 miss out of the window such that it can fetch more instructions, so it can actually make progress in the program instead of stalling. And while it's making progress, it can discover this load 2 instruction. And if this load 2 instruction is independent of the load 1, it can actually be executed, and it can generate its address, and assume that it's the cache miss over here. It can generate that cache miss. That cache miss starts getting serviced in parallel with the original cache miss. When the original cache miss returns, what the run-ahead processor does is it flushes its pipeline, restores the checkpoint, the program counter, load 1's program counter, restores the register file state at that point, and then re-executes load 1. Now it's a hit, and then it keeps re-executing instructions. At some point it will re-execute load 2, and now it will hopefully hit in the cache, because its miss was initiated during run-ahead mode instead of stalling the processor. And the benefit is that now you get saved cycles because you've executed the program much faster. Basically what you've done is, instead of stalling the processor, you've done prefetching, right? You could think of it that way. And you use the main thread as a mechanism for prefetching. It's speculative because you do not know if you will keep executing. And you do not have the full data values available to you, because there are some instructions that are cache misses. They're not complete yet. Yes?
So when you checkpoint, you're not saving the entire actual state. You're not saving like the reservation stations.
No, you don't need to.
So,
That's right.
So when you go back at the end of run ahead, so if you have like a really short run ahead period, you could like lose instructions.
That's right, exactly. And that's the downside of the approach. So if this run-ahead period is not long, or if it doesn't, more generally, if it doesn't provide any benefit, what you're really doing is you're really flushing your pipeline. And this penalty over here can reduce your performance. And we've discussed why a run-ahead can be actually inefficient, right? There are 3 reasons why this may not provide benefit. It could be short, as we've discussed. It could be overlapping with a previous run-ahead period, because you may have dependent cache misses. And you enter run-ahead for 1, and then enter run-ahead again. You execute the same instructions. Or it could be just useless. Basically, you run ahead, and there are no misses discovered. No new misses discovered. Then there's no benefit also. Okay? So this could degrade performance, absolutely. So that's why you need efficient techniques that can estimate whether it will degrade performance or not degrade performance and enter appropriately. Okay. What else? There's actually a run-ahead question in, was it the final last year? Or the second midterm? So you can take a look at that. That's a good question to solve, to see if you actually understood the concept. It's better to solve it before Wednesday than after Wednesday, probably. So this is a relatively simple mechanism compared to designing a large instruction window. That's why this has been used in IBM Power 6, for example, or Sun Rock, and maybe some other processors too. I wish everyone described how their processors actually operated. That would be really nice. Yes?
Did you say you were going to say something about the next lab?
Next what?
About the next lab.
Next lab? Did I say that?
It's okay.
Oh. No, I didn't say that, but
Okay.
next lab will be fun. I'll say that, I guess. We'll talk about the deadline for the next lab later.
Okay.
Right now, focus on the exam. So we will give everyone. The same deadline, basically. Late labs won't count for the last lab because we're hitting the end of the semester, right? Yes. You say it again? You can't use. That's right. Yes, that's what we discussed in I guess a few lectures before, right? Yes, you cannot use late days because if you use your late days, then you'll be done probably after the end of after when the grades are due. And that's not what we want. But I can give you cookies. 1 cookie per late day. Is that good? If you're really upset about it. Well, you cannot push it beyond some point.
Right. And I was thinking that point is
Oh. Well, you cannot. Well, don't worry about it. Basically, don't worry about it. You'll have enough days, I think. If you don't, I'm sure I'll give you some cookies. That's actually not bad, right? If you saved a lot of late days, you'll get a lot of cookies. And your favorite cookie. What do you think?
Sounds good.
Sounds good. If you overuse the late days, you give me a cookie, though.
Is that a trade we can make?
Say it again?
Is that a trade we can make? Like I can bring in a
Sure, maybe. We could try that. Depends on the quality of the cookies, though. How stale the cookies are. If you've been saving the cookies for 2 years, I don't want them. What else? Now, we've covered a lot of exciting topics, actually.
We get a note sheet for the midterm.
Say it again?
Two-sided note sheet.
Yes, two cheat sheets.
Okay, two-sided.
Two-sided, yes, two-sided. The same instructions apply,
Okay.
except you double them.
Are we going to get 3 for the final? Or
Yes, you're getting 3 for the final.
What should we put
What should you put on
on?
them? Whatever you like. I'm fine with whatever you put on them, frankly. I'm not going to check them. Oh, what should you put on them? I wouldn't put anything on them. I don't know if that's the answer you want, but I don't think you need it.
Making them is like enough of like practice.
That's right, exactly. I think making them could be good practice for you. I would put some keywords, for example, that could be useful.
Just print out that list per se.
That probably will require more sheets than you have.
All the key.
All the buzzwords. That's another good way to study for the exam, going through the buzzwords. But I would go through the slides for sure, and think about the trade-offs. Yes.
So the demo for this lab is on Friday, right?
That's right.
But if you're using 7 days on this lab, it's going to be due on Sunday. So can we demo the week after that? Then?
So I'll let you discuss that with Rachada and the TAs. I think as long as you demo and you show that you've done the work, we're okay. But you should set the deadlines, okay?
Yeah, so I mean, at some point we want to have office hours or hours that we can be around, and we for lab 7 to be able to before you set aside some time to find each but before now to think of the other keys might not be able to.
And the studying you do for this exam would be useful for Lab 7. I definitely recommend that you study coherence protocols for this exam. What else? Are we done? Any other questions? So many? You'll be okay? I think you'll be okay too. Just know things well. The most important thing is that you learn the concepts. Even if it's after the exam, that's good. If it's before the exam, that's even better.
Graduating is pretty important.
That's also important, yes. I agree. But some of the things that you learn in this course will hopefully be useful for you, like whatever you do. And I think the trade-offs that you make are really the key parts of this course. Like that. That's why I think Lab 7 is very important, because you'll be implementing a coherence protocol that's used by, or a variant of which is used by pretty much any processor that's out there in the market today, or any high-performance processor, I should say. MESI protocol is used by pretty much any processor. So you'll be doing that. Isn't that exciting?
So
Yes.
do real processors actually use the directory-based protocol? It seems like there's a lot of overhead associated.
Yeah, actually real processors do use directory-based protocols, especially if you want to build a scalable system. Large-scale multiprocessors use the directory-based protocol because there's no way to scale the bus beyond, let's say, 16 cores. We'll talk about interconnects. There is overhead associated with it, but they deal with it. Unfortunately, the directory size can be very large. And people try to reduce the overhead of the directory with many ways. Instead of having a bit vector, for example, they try to have Bloom filters. That's one example. They try to have compressed representations of which caches actually have this block. But that is really the only way to scale cache coherence to a very large number of cores today, because the interconnect is not scalable. And we'll cover that in interconnects. Okay, I guess no more questions. I guess study hard and arrive 5 minutes early. And good luck.